Alright, continuing ME 627, we did the phase space, phase portraits, we did a 2D example sketched by hand, and then we said we'll find equilibria. So autonomous case we are going to study in some depth. Q dot is equal to f of q if q star is a fixed point. That means f of q star equals 0, then q is equal to q star plus xi, this one being infinitesimal, leads to xi dot is equal to d f of xi at xi star. So this is a matrix. That's not what I mean at all. What I mean q at q star times xi. Okay, and that leads to our study of the system x dot equals ax, a constant matrix of size n by n. Alright, we write determinant of a minus lambda I equals 0, we get a polynomial, we get n values of lambda including multiplicities. The repeated eigenvalue case is a little more complicated. For the moment we will avoid that. Assume lambda 1, lambda 2, lambda k real part greater than 0, lambda k plus 1, lambda k plus 2, lambda m real part equal to 0, and lambda m plus 1 to lambda n real part less than 0. What that means, these give growing solutions. This means what does it mean? This means fixed point unstable. If there is any eigenvalue whose real part is greater than 0, it is guaranteed that that fixed point is unstable. These require, well, because we are linearizing some system, so they require further analysis. For the linearized part, they don't require. This is what it is. It is only over here that we have some problem. Over here also, if we have let me see, if repeated, then they require further analysis. If distinct, so plus minus I plus minus 1.7 I. See, 4 eigenvalues is an example. 4 eigenvalues, real part 0. For the strictly linear system, no further analysis is needed. If this is actually a linearization, then further analysis is needed. However, if we have, let's say, another example, plus minus I plus minus I. See, over here we have to see, because they are often unstable in a weaker sort of way. Now, these solutions decaying solutions. Okay, all right. Now let's consider subcase, real eigenvalue. Okay, so when we have a subcase of a real eigenvalue, say lambda greater than 0, a u is equal to lambda u for some u, then in the space of Q, well, this actually goes all directions. So let us say this is Q1, this is Q2, and I'll just indicate a dot 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 here and write Qn. Let us say this here is the vector u. Okay, in that case, a trajectory that begins on this point, lambda is greater than 0, will move away in this direction, and a trajectory that begins here will move away in that direction. This is actually a one-dimensional subspace, and it's called an invariant subspace because an initial condition that starts in this subspace continues in this subspace, remains in the subspace. Okay, all right. Suppose we have a different situation, say sigma less than 0, AV equals sigma V for some V. Let us say here is V, this is V. Remember, U need not be perpendicular to V. Okay, eigenvectors of symmetric matrices are either orthogonal, or in the repeated case they can be chosen to be orthogonal, but over here this is that orthogonality condition is not necessarily true. So over here what happens is, if I have some initial condition that is on this eigenvector, it goes towards 0, stays on that eigenvector. If I have an initial condition here, it goes towards 0 like this. This is also an invariant subspace. Okay, so the real eigenvalue case is clear. Suppose the eigenvalue is 0, that's real also. Let us say a eta equal to 0 for some eta. In that case, now I'll use a red color here. So let us say that direction is eta. Then if you start there, you stay there, you just sit there, because there is no rate of change. That also is an invariant subspace. Okay, so we've covered the real eigenvalue case. Now let us go to the, well, let's go to the complex eigenvalue. Okay, so as you know, because A is real, so these will occur in complex conjugate pairs. So say A plus IB is an eigenvalue, A and B are real, then A times some vector u plus iv, different uv, not the previous one. A u plus iv is equal to A plus ib times u plus iv. U and v are real. This tells you, if you are familiar with complex arithmetic, that automatically AU minus IV is going to be A minus IB times U minus IV. That means A plus minus IB are the eigenvalues, U plus minus IV are the eigenvectors, but the eigenvectors are complex. What does that mean? For real solutions, if you go to the space of Q again, so that's Q1, that's Q2, and dot dot dot, that is Qn, that's your origin. In that case, let us say this vector is U, and let us say blue, this vector going to the origin V, this line, sorry. So this U and this V U and V define a plane and trajectories stay inside that. So if A is less than 0, what happens is trajectories in the UV plane go towards origin. Whether it is counterclockwise or clockwise depends on how you are looking. So this is the A less than 0 case, and if A is yellow, if A is greater than 0, then it may be spiraling out. Well, I should have put an arrow there, otherwise it doesn't even mean anything, but now, so it could be spiraling out. Spiraling out and spiraling in. Okay, this is the sort of thing that you will see. How do you know that it is spiraling, and how do you know that it is invariant? This is also an invariant subspace. Okay, so how do you know that that is true? Well, if you say let x be equal to alpha u plus beta v, then x dot is equal to ax is equal to alpha au plus beta av. Now what happens to au and av? You need to come back here. You see, you look at this equation and you separate it into real and imaginary parts. You get au is equal to little au minus bv, and you get av is equal to bu plus av. And so you see, capital A times u is some linear combination of u and v, and capital A times v is some linear combination of a and v. That is why when you come here, this is some linear combination of u and v, this is some linear combination of u and v, and so you are ending up with linear combination of u and v. This means the rate of change is in this plane, stays in the plane. Okay, that is what gives us a picture that looks something like this. You may have one invariant subspace like this, let us say, okay, let us say lambda equals 1 and lambda equals minus 0.3 plus minus I. Okay, just as I'm making these numbers up, but you can see. So for this one, this is the eigenspace, the invariant subspace. This one, there is another subspace. For this one, we have, let us say, this direction. Okay, this part is unstable, this part is stable. Okay, and so if you have some initial condition, for example, if you have an initial condition that is in this plane, then it will spiral in like that. But if you have an initial condition that is a little bit off, it's a little bit above this plane, then it will be spiraling in, but it will eventually sort of go off in this direction. And if you have another initial condition that is below the surface, then that will also be spiraling, but it will eventually go off in the other direction. Okay, so this is the sort of behavior you will see in phase space when the eigenstructure is like that, right? So eigenvalues positive real part, unstable, sometimes we say unstable eigenspace also, sometimes we say unstable eigenvectors, 0 real part. This leads to something called a center. Okay, and negative real part leads to stable eigenspace. Now what I want you to realize is that if there are any such eigenvalues, then that equilibrium is not very interesting, it's unstable. Okay, so you won't see anything there, trajectories won't stay there. And if there are any of these will decay out. And when there is something like this, that is the part that will stay, and the presence of nonlinear terms make further analysis necessary, okay, needed for sustained oscillations. Okay, some eigenvalues with 0 real part are needed. How many? Complex conjugate pairs, right? So at least 2. Okay, now in the nonlinear case, what will happen? So 1 lambda less than 0 and lambda equals plus minus I omega, this case. Okay, so in this nonlinear case, what may happen is typical case, for example, is that this complex conjugate pair has some invariant subspace, that's called the center subspace, and this eigenvector has some stable direction, and arbitrary initial conditions lead to trajectories that sort of settle down here and give you oscillations. Something like that. Now, it won't be exactly on this plane because of the presence of nonlinear terms. So in the presence of nonlinear terms, what will happen is that this space, this will bend. It will locally be tangent, so you may have something that bends in this way, and the trajectories will be on this surface. Let me see if I have space to draw something like that. I just have enough. So you may then have something that looks like this, a sort of bent surface of some kind, and on this locally at that point that will be a tangent, and on this you will have something that will come in and do something like this, and maybe it will evolve slowly because of nonlinear terms, and you may have some other trajectory coming from below which sort of also follows that and sort of settles over here, and this is then called the center manifold. We will not spend much time in this course computing what the center manifold is, but you can see that there will be two state variables involved on the center manifold, and this is really the main reason why we will spend quite a lot of time in this course studying this system, right? This is at the heart of what happens when there is one lightly damped mode. Nonlinear terms are important. Other modes are damped strongly, and then you study this, and as you will see, there are interesting things to be studied even in this highly simplified system. So I will remind you of my earlier warning that this course will not help you immediately solve truck vibration problems, but I hope you will agree soon that even the study of this has things to teach us. Thank you.